Welcome to the lecture on variation. There are three types of variations that we're going to talk about today. The first type is called a direct variation. And this is a relationship between two variables. We say that one variable y varies directly as another variable x, or y is directly proportional to x if there is a non-zero constant k such that y equals k times x. K is called the constant of proportionality. So k is just a number, and what you have is one variable y is just a constant times your other variable. So if you are given a problem that involves a direct variation, they're going to have to tell you enough information so that you can first figure out what the value of k is, the constant of proportionality. And once you find k, then you can answer the actual question that's being asked. So for example, if we have x varies directly as y, and x equals 10 when y equals 7, find y when x equals 50. So the first thing we want to recognize is that the problem says x varies directly as y. Whatever variable is listed first is what is going to go on the left side of your equals. Whatever variable is listed second is what gets multiplied by your k. So in this case, x equals k times y. That's our direct variation. That's our relationship between x and y. So the first thing we're going to do is try to figure out what k is, and they will have to give us in this problem an x and a y that go together so that we can figure out what k is. So in this case, x is 10 when y is 7. So once we've set up our relationship here, what we're going to do next is substitute in 10 for the x, 7 for the y, and that should enable us to solve for k. So we're going to divide both sides by 7, and we get k equals 10 sevenths. Now what we're going to do is rewrite our direct variation by substituting in the value of k. So x is always going to be 10 sevenths times y. So if we know that relationship, then to answer the actual question, we want to find y when x is 50. So all we have to do now is substitute in 50 for x, and we're going to solve this for y. Now how do we solve this equation for y? Well, we can just multiply through by the denominator that I see. I've got a 7 in the denominator. So if I multiply through by 7, 7 times 50 is 350. The 7's cancel out on the right-hand side, so we just get our 10y. And now I can divide both sides by 10. And that's just going to cancel out my zeros, so y equals 35. So when we do these variation problems, we're going to first set up our generic formula, our relationship between x's and y's. Then we're going to substitute in an x and a y that go together, and that will enable us to find our constant k. Substitute k back into the original relationship, and then substitute in the value that they're giving you so you can find the missing variable. So we're going to try another direct variation problem, but this time it's sort of phrased in the context of a word problem. So here we have, in the study of electricity, the resistance of a conductor of uniform cross-sectional area is directly proportional to its length. Suppose that the resistance of a certain type of copper wire is 0.640 ohms per 1,000 feet. What is the resistance of 2,500 feet of the wire? So the first thing we have to figure out is our relationship between our variables. So step one here is to kind of write a generic formula. So in this first sentence, it tells us that the resistance of a conductor of uniform cross-sectional area is directly proportional to its length. So the variables that we're dealing with here are resistance and length, and it tells us that resistance is directly proportional to its length. So remember, whichever variable is listed first, which in this case was resistance, is on the left side of your equals. Whatever variable is listed second, which in this problem was length, is what gets multiplied by your k. So our resistance is directly proportional to its length. So R equals k times L. So that's the overriding formula that we're going to use. Now we need to find out what K is, so we need an R and an L that go together, and that's what this 0.64 ohms and this 1,000 feet are. So in step 2, we're going to substitute in 0.640 ohms. That's a resistance, so that's 0.64 for my R, and my length was 1,000 feet, so I'm going to substitute in 1,000 for my L. So if I divide through by 1,000, 1,000 has 3 zeros in it, so when I divide any number by 1,000, that's going to move your decimal place 3 spots to the left. So K here is going to be 0.00064. So we now know what K is. Let's substitute it back into our original relationship, and now we have the resistance R is always going to be 0.00064 times our length. So to answer the actual question, we want to know what is the resistance when we have 2,500 feet of wire. 2,500 feet is our length. So we know what L is, we're looking for R. So we're going to leave R in the problem, and we're going to substitute in 2,500 for RL. So if we go to our calculator, we're just going to type in 0.00064 times 2,500. Hit enter, and we get 1.6. So R equals 1.6. Now you want to put units on your answer since this is a word problem. And if you remember from earlier when we were talking about resistance, this 0.64 had units of ohms. So that's going to be the same units that we're going to use for our answer. So our answer is 1.6 ohms of resistance. And there's our solution. Okay, so that's called a direct variation, when your first variable is a constant times your second variable. Our next type of variation is called an inverse variation. So we say that y varies inversely as x, or y is inversely proportional to x, if there is a non-zero constant k such that xy equals k, or in other words, y equals k divided by x. So if you remember from our direct variation, we had y equals k times x. In an inverse variation, we're going to have y equals k divided by x. So whenever you see the word inverse, you want to divide by your second variable. Whenever you see the word direct, you're going to multiply by your second variable. So that's the big difference between these two variations. Okay, we're going to treat these problems just like we did the last ones, except that the initial formula that we're using is going to look a little bit different. So for example, if we have t varies inversely as s, and t is 3 when s is 5, find s when t equals 5. So right off the bat, we know that t varies inversely as s. So whatever variable is listed first is going to go on the left side of your equals. And since this is an inverse variation, we are going to have k on top, and underneath the k, or divided underneath that k, is our second variable, which in this problem was s. So our relationship here is t equals k divided by s, because we see the word inversely. So there's our relationship. Step 2, we need to find k, so we need a t and an s that go together. So when t is 3, s is 5. So let's substitute those in. I'm going to put in 3 for t, put in 5 for s, and now to solve this for k, all we have to do is multiply both sides by 5. 5 times 3 is 15, so k is 15. So now what I'm going to do is rewrite my initial relationship, substituting in 15 for that k. So t equals 15 divided by s. And step 4 is to solve the actual problem. We want to find s when t is 5, so I'm just going to substitute in 5 for t. We're looking for s. So to solve this, since s is in the denominator, we need to clear out our fractions, so I'm going to multiply both sides by s. We're essentially cross-multiplying here. So the s's will cancel out on the right side, giving me 15. On the right side, 5 times s is 5s. And now I can solve this for s by just dividing both sides by 5. So s equals 3. And there's our solution. So an inverse variation, you just have your first variable equals k divided by your second variable. So here's a word problem using an inverse variation as well. We have pairs of markings a set distance apart are made on highways so that police can detect drivers exceeding the speed limit. Over a fixed distance, the speed r varies inversely with the time t. In one particular pair of markings, r is 45 miles per hour when t is 6 seconds. Find the speed of a car that travels the given distance in 5 seconds. So, step 1, we need a relationship. So if you go to this middle sentence here, it tells us that r varies inversely with time t. So since r is listed first, that's on the left side of our equals. Since it's an inverse variation, we're going to have a fraction. The constant k is on top, and our second variable, which was t, is divided into that k. So here's our inverse variation. Step 2. To find k, we need an r and a t that go together. They tell us that when r is 45 miles per hour, t is 6 seconds. So let's substitute those two values in. So 45 is r, t is 6. I'm going to multiply both sides by 6. So the 6's cancel out, and I get, if I go to my calculator, 6 times 45 is 270. So k is 270. So let's rewrite our inverse variation, substituting in k. So r is going to be 270 divided by t. And now to answer the actual question, it says find the speed of a car that travels the given distance in 5 seconds. So 5 is what we want to substitute in, and since it's seconds, that means it's a time. So we're going to let t be 5. So I'm going to substitute in 5 for t. And if we divide here, 270 divided by 5 gives me 54. And remember what we just found here. We were finding the speed of a car, and the units that were used for our speed earlier were miles per hour. So we're going to be consistent with that, and our answer would be 54 miles per hour. So if that was underneath the speed limit, then the car would be fine. If the speed limit was 45 miles per hour, then this car would be speeding and could, hypothetically get a ticket. Okay? The last kind of variation that we're going to look at is called a joint variation. And a joint variation is a little bit more vague than the last two because lots of different possibilities could happen. So a joint variation basically says that if a ratio of a variable y to the product of two or more variables, possibly raised to powers, is constant, then y varies jointly as or is jointly proportional to the other variables. So what does all of that mean? Basically what you want to imagine is your first variable y is supposed to be in a ratio. A ratio means a fraction. So the ratio of y to the product of two or more variables possibly raised to powers. So we're creating a fraction. The y is on the top, and on the bottom could be all kinds of variables possibly raised to powers. So that's where the variation is here. We don't necessarily know what's going to go in that denominator. It changes from problem to problem. So you're going to get your y over your variables, and that is the constant k. Okay? So that's what a joint variation looks like. Let me give you an example. It says, if f varies jointly as g squared and h, and f equals 50 when g equals 4 and h equals 2, find f when g is 3 and h is 1. So we have F varies jointly as g squared and h. So the first variable is f. That's the one that goes on top. In the denominator, since we're varying jointly, are your other variables. And we have a g squared and an h, and we want the product of those two in the denominator. So f came first, it goes on top. The g squared and the h go on the bottom. And this whole thing is equal to our constant of proportionality k. So this is what our joint variation looks like. F over g squared h equals k. Once we have that set up, we're going to solve it just like we've been doing. So let's substitute in f is 50 when g is 4 and h is 2. So I'm going to put 50 in for f, 4 in for g, and remember that's getting squared, and h is 2, and all of this is supposed to equal to k. Now if you're going to type all of this in your calculator at once, you want to make sure that you put parentheses around this whole expression in the denominator. So you're dividing all of that into 50. So the correct way to write this would be 50 divided by, whoops, a typo there, 50 divided by parentheses 4 squared times 2. Close the parentheses. So there's our k. So k is 1.5625. Now that we know what k is, let's substitute it back into our joint variation. So f over g squared h equals 1.5625. And now we can answer the actual question. We want to let g be 3 and h be 1. So I'm going to leave f as f, substitute in 3 for g, and remember that gets squared. H is 1. And this denominator down here is easy enough to simplify. 3 squared is 9. 9 times 1 is going to stay 9. So to solve this, all we have to do is multiply through by that denominator, and we'll find out what f is. So if we take our 1.5625 times 9, there's our value of f. Whoops, I hit enter too many times there. So our answer is 14.0625. And there's our f. Okay? Now the last example that we're going to do is not really a new variation, but it's a combination of all the ones we've done. So remember, for direct variations, you have y equals your constant k times x. For an inverse variation, you have y equals k divided by x. And for a joint variation, you have y over a bunch of variables equals to k. So in this last example, we're just combining all of these together. So you want to look for those keywords, direct, inverse, and joint, to decide whether we should be multiplying by k, dividing underneath k, or dividing underneath our y. So if we look at this example, it says the volume of gas varies inversely as the pressure and directly as temperature. So let's go ahead and work with that right away before we start reading the rest of the problem. So it says the volume of gas, I'm going to call that V, varies inversely as the pressure. So let's just stop right there. If we know that the volume varies inversely as the pressure, then the volume came first, so that goes on the left side of your equals. And for an inverse variation, we have K on top, and the pressure P would be underneath it. So there's our inverse variation. In addition to that, it says the volume V varies inversely as the pressure and directly as the temperature. So I'll call temperature T. And since temperature is in a direct variation with our V, remember a direct variation you multiply by K. So in my relationship up here, I'm going to put that temperature T multiplied times my K. So here's the direct variation, K times T, and here's the inverse variation, K divided by P. So this is a combination of both an inverse and a direct variation. So here's our relationship between all of our variables. Now we're going to need a v, a t, and a p that we can substitute in so we can solve for k. So that's what the next sentence is going to tell us. It says, if a certain gas occupies a volume of 1.3 liters, so V is going to be 1.3 liters, 300 degrees Kelvin, that's a temperature, so T is going to be 300 degrees Kelvin, and a pressure, so that's our P, of 15 newtons per square centimeter. 15 newtons per square centimeter. So these are our three different values that we're going to substitute in. So let's go ahead and do that. For V, I'm plugging in 1.3. We're looking for K, so that stays K. Temperature T was 300, and pressure P was 15. So to simplify, let's go ahead and find out what 300 divided by 15 is. That's 20. So we get 1.3 equals 20K, so we just divided these two, and now we can divide both sides by 20. So if I do 1.3 divided by 20, then my K is 0.065. So now we know K, so let's substitute that back into our original variation. So V equals 0.065 T divided by P, and now we need to substitute in the values that they give us so we can find our missing variable, and that's the end of the sentence here. Find the volume, so we're looking for V, at 340 degrees Kelvin, that's your temperature, and a pressure of 24 newtons per square centimeter. So we're letting T, the temperature, be 340, and we're letting our pressure P be 24 newtons per square centimeter. So we're looking for V, I'm going to leave that V, and I'm going to substitute in 340 for T and 24 for P, and if I substitute that into my calculator, we want 0.065 times 340 divided by 24. So our answer, we're going to have to round this off a little bit. I might say it's 0.9208. So our volume is 0.9208. And what were the units on our volume earlier? Remember, our volume was 1.3 liters. So that's going to be the same units that we want for our solution. So our answer is 0.9208 liters. All right, that concludes our lecture on variation. Good luck.